Alright, so last time we talked about the phase diagram and water at its triple point and how that was easily accessible in just your average everyday home, assuming you had access to a stove that could heat up the water to the boiling point, pushing air out of the system, and once we close that, it's just water and water vapor, and landing us on the curve of the phase diagram between liquid and the water vapor at equilibrium. Then going back towards the triple point, we could then just stick that system into the fridge, and therefore after some time passed, maybe some ice is formed, and boom, we hit the triple point. But in this video I want to discuss how that process is related to something known as the Antoine equation. So let's actually go find out what that is. So I'm just gonna go ahead and Google it. The Antoine equation. All right. So the Antoine equation, it's a semi-empirical, which means that it's based on both theory and experimental data. And it's basically just relating, it's a relationship between pressure, right here, vapor pressure and temperature for pure substances. And why is that relevant? Well, the water we had was a pure substance, and the whole problem of that last video was trying to get it to a pure substance and getting the air out of the system. And you notice it's derived from the Clausius-Clapeyron relation. And that's just basically another relation saying that there's no linear relationship between uh, vapor pressure and temperature. In fact, there's a sort of curve to that. And this Antoine equation basically gives us some parameters we can use that are also experimentally determined based on certain conditions right here. And we can use those to basically find our pressure at any given value. But today's video is going to be more focused on finding or actually using nonlinear and linear regressions to map out some data we have to this model, the Antoine equation. So in doing that, we're going to have to find some data, and thanks to our very generous professor, thank you, Carlos, we have on GitHub this CSV file that we can download. You're probably wondering, what is GitHub? Well, it's a very highly developed platform, contains millions of repositories, including Carlos is where he uploads all his things we do in class, and right here we have our data. And what I'm going to want to do is find the raw, and here we have the raw data file, .csv file, containing our, I believe, the temperature on the left side, which is our in Celsius, and on the right side we have our pressure in millimeters per mercury. So in graphing this, what we're going to use is something called collaboratory. I'm just going to go ahead and that something right here. That's awkward. Let's not use this. Let's go ahead and make our own quick. I'm just going to highlight and delete that. And okay, good to go. So the first thing we're going to want to do is use the exclamation character, and that's going to tell, actually, let's start with explaining what Collaboratory is. So Collaboratory is actually a Jupyter notebook, which means it's open source, hosted in Collaboratory, of course. And what's nice about it is that we can pretty much just openly code Python in our browser, and it pretty much bypasses all those little things about having to install Python based on your device, whether you have Windows or whether you have you're a Mac user. Everyone can just come on Collaboratory, and like Google's other services, anyone can basically make their own code here. So again, we're going to use the exclamation mark, that denoting that we're going to tell the underlying operating system, the OS, we're going to do something in here within Collaboratory, and we're going to use the very famous command wget, and this is a, I believe, Unix-like command. Basically, actually, let's just go ahead and find out what those are, Unix commands. So here we'll find wget, and actually it's by GNU, and that gets into some sort of wacky stuff about GNU is the acronym for GNU not Unix, and it's like a Unix-like command. I won't get into that, but basically all you have to know is about wget. We get web content, Actually, yeah, we just get web content, isn't that it? All right, and then since we have our web content right here, the .csv file we got from GitHub, we're gonna go ahead and paste that URL, and I'm gonna shift enter, and what it's gonna do is download that real quick. And if we check our file manager, oh, we actually have two. Let's go ahead and just delete that one. So we just have one. You know what? I'm gonna delete this and just something really important that happens sometimes is that if you don't, if you reload some commands and you'll get an error, what you want to do is hit that, what I just did, runtime factory reset, and it's just gonna re-download the code right there. So now we just have one. That just hopefully we don't get any errors from that double overlap from my little practice run earlier, but all right, let's get going. So what first thing we want to do, well, we have data. What do we want to do? Graph it, of course. So we're going to use NumPy, and NumPy is a very nice Python laboratory. It's numerical Python, and you can do a bunch of things like, well, mainly we want to focus on our indexing and sorting of arrays pretty much in this course with NumPy, and I believe there's a lot of other mathematical functions that we'll be using, but yeah, that's what NumPy is. And then I put as NumPy, that's just an alias. I could technically call this whatever I want. I could call it me, JA, but widely known alias or use alias is just NP as NumPy. Great, so we imported NumPy, and what we want next is to have the data displayed. So let's make an array. So an array is very nice for displaying very like or similar types of information, types of data. That is just the variable. I'm going to call that array. And it's going to have an array with that information. So to load that information, we're going to do something called np.loadText. So np.loadText, this is a function going to contain some arguments I have to use. np.loadText right there, it loads data from a text file. So we have that .csv file, and that's going to be pretty important later on. But right now, we just want to load the file name. So that is water vapor pressure.csv. And then within, like I said, within np.loadText is a function with parameters that we have to use. NumPy is actually pretty smart. So if you don't, I mean, normally you would have to, when making your own function, you have to make sure it has all the parameters you have whenever you're doing something with it. But in this case, NumPy is pretty smart, and it will just set the things to default if you don't input it. So I'm just going to go ahead and skip that comments, and we see converters, skip rows. Actually, I want to talk about this delimiter. What is the delimiter? Okay. So the important thing about this file, it's .csv. .csv means that it's comma separated values. Now, if I just left it alone, we'll see what happens. The delimiter is a very nice argument that helps us pretty much find and separate values whenever we need to. But I'm going to get an error here because it's a .csv file. There's commas in there, and NumPy doesn't know how to convert a string, that comma, to numbers since there's a comma there. It's separating the value. So what we're going to do, delimiter is a nice parameter we use to go ahead and separate those comma separated values. Pretty neat. Oh, what did I do? Delimiter, oh, equals, sorry. Syntax. And now we can actually call that array we just made data, and it will have all those nice values we just found right here. I just match it up, 2.93, yep, checks out. Cool, now we have this array. Okay, so how do we actually graph it? Well, the neat thing is with arrays and with NumPy, we can actually assign variables. So, okay, we have the left column as our temperature. I'm just going to call it T. We're going to assign a variable to it. How are we going to do that? We're going to use the array, and inside the array, we're going to use from the start. Now, indexing in arrays is pretty important, but mainly what I want you to get out of this is that within the array, we're going to call from start to finish. So the thing about with arrays, if you don't call it, if you don't put a value there, it'll just start from the start. And likewise, if you don't put a value at the end, it will just go to the end. So it's going to go from the first row, indexing at 0, to the last row. And then I'm going to separate that to find another thing. And I'm going to call the column. And again, indexing starts at 0. So the first column is 0. And actually, I need to make sure it's calling it from the data array. So I'm going to go ahead and shift evaluate that. Actually, you're not going to see it because I didn't put it. So T, now we call it. Now it should match the left-hand side, Celsius. Now we need to do something similar for the pressure. We're going to do P equals data. And then our array, same thing. We don't care about the rows, but we do care about the column. So we'll shift evaluate that and then check our pressure. It should be different, yep. And it'll start at 2.4, 2.4, perfect. Make sure I'm recording that. Okay, cool. Cool, but the pressure isn't exactly what we want from the Antoine equation. If you actually look at the Antoine equation, what is it? Well, let's find it. It is the log base 10 of P. And that's what we want. Log base 10 of P. All right, cool. So how do we do that? Well, we have numpy, and might as well just change this variable name to log base 10 of P while we're at it. But with numpy, we also have some mathematical functions we can use. So I'm going to do np.log base 10 of the array. And what that's going to do will be different values this time of the pressure, but it'll take the log base 10 of those values. See now that they're different, 3.3, 2.4. All right, cool. Now that we have those values, we need to graph them. Since we have assigned the variables into their own separate little, we assigned the data points to their own separate variables, and we need to graph them. So how are we going to graph them? Well, there's something called Plotly. Actually, let's go ahead and look that up. Plotly. Plotly is a plotting library for Python, and I don't think it's the right one. Plotting library for Python, and it's widely used, just like NumPy. There's actually a lot of professional stuff that goes on here. You'll see statistics, scientific charts, financial charts, and what we're interested in is subplots. And while look at it, there's just so much you can do with Plotly. But in our case, since we just want to graph our data points, we're going to use something called subplots. Now, if you look at subplots, subplots are basically used for layering information. You're comparing different types of data so you can just see the connection better. In terms of comparison, subplots are probably the best thing we're going to use as of right now. It's for everything in the scientific field, you're just going to want to compare, especially in this case, we're going to compare our data to models that we're going to make. But yeah, subplots are what we want to use for that. So what we're going to do is to make a subplot, we have to go from Plotly. And it's nice because Plotly is supported by Python, at least in Collab. We don't have to install anything crazy. So from plotly.subplots, we're going to import make subplots. So that's just allowing us to make some subplots. All right, cool. And now let's make a figure with our data. Let's just call it figure 1. How about that? Figure 1 equals make subplots. That's right. Make subplots. So now we have a subplot for figure 1. And let's go ahead and add, I believe it's add scatter. Yep. Add scatter. Oh, I forgot this. Make sure, I always forget. Make sure whenever you're writing out a function, parentheses are always needed for evaluating it. Still learning the syntax, but yeah, parentheses after a function when you evaluate it. Figure 1.addScatter. So again, functions use parameters, and I didn't put any parameters in the line of code right here because, you know, NumPy is pretty smart and it just has defaults if you don't put anything in. But here's actually where we need to input the data. So we have our X and Y. So X is our temperature, or actually just T. And y, what is our y? Y is our log base 10 of p. Now, if I shift evaluate at, oh, another. Make subplots is not defined. Oh boy, where did I make a little mistake again? Make subplots, make subplots, subplots. Not log 10. Something is wrong. Oof. Alright, I'll back. I just sorted out. Oh, sorry about that little interruption. I think I know what it was. I did not evaluate familiar. Yep, there it is. Okay. Classic syntax. So make sure also you shift evaluate whenever you add new code, and especially if your next lines of code are dependent on it, you need to evaluate that before you can run the next code, or else it won't know where it's coming from. Make sure you keep on check every little thing, because there's always a lot of things you can mess up on. But anyways, going back to, okay, so we graphed our data onto this nice little graph plotly allowed us to make, but you can see it's lines. And with data, we don't really use lines to represent data. We use markers. So we're going to change this to mode equals markers. And that will give us them in markers. Nice. And we have, you can see a little trend right there. Pretty nice. But I'm just going to go ahead and do this now. It's a little too bright for my liking. And in our class, we have, I think, pretty good consensus on that. I think everybody uses the dark default background, so that's exactly what we're going to do. So let's see, how was this? It was going to import plotly input output as PO, and that will let us, evaluate. Well, good to do that anyway. PO dot default or templates default. So we're actually just going to call the default templates in plotly, and that's equal to our one of the templates. If you go on the website, is plotly underscore dark, and if we evaluate everything, it should turn dark. Nice, perfect. So we have our data plotted. Next thing we gotta do, we'll start with nonlinear regression. So remember what nonlinear regression is. We're minimizing the sum square errors of our data from our model. So it's going to be the difference between the model and the data. The difference, we're going to square that, sum it, and minimize it. So let's go ahead and just start with, well, minimizing. How do we minimize something? So again, there's a nice little library we also have. I believe SciPy, Scientific Python, excuse me, it builds on NumPy. It's a little slower, but it allows us to do more in-depth sort of mathematical functions, computing tools like minimizing. So we're gonna go ahead and do that. SciPy.optimize, import, oh, sorry, it should be a from. Catch SciPy.minimize, import. We're gonna import minimize. Okay, cool. Let's go ahead and define our sum square error. So we're going to define a function that returns us a vector array. And in that vector array, well, what's going to be in it? What are we trying to minimize in our function? So, well, we have pressure, we have temperature. So what else do we need? We need A, B, and C. We need to somehow minimize A, B, and C so that they fit within, or they match our parameters of our experimental data of P and T, our pressure and our temperature. That was the log base 10 and temperature in Celsius, pressure in millimeters per mercury. So before I get what I'm going to do, I'm going to, let's see. yeah, let's set the vector equal to our parameters, and these parameters obviously are going to change depending on what temperature you're at right here. Yeah, make sure you watch your parameters, and it looks like it changes with the substance you're using. So assume if it was water, make sure you're using these certain parameters for under these ranges of temperature, again in Celsius, and just look at how it changes. So again, something to keep in mind when you're calculating that. Okay, so going to define the function, define our sum squared error, a, b, and c. The next thing we want to do is minimize. We want to minimize the difference between our data, our model from our data. So let's go ahead and get that sum square error. What is the sum square error? So we'll go back. Here we go. A minus b over c plus t. That is actually our model. If you notice, we have pressure. It's equal to the pressure, and we have the pressure. So this is going to be our model, and this is our data. We're going to subtract the model or the data from our model. So let's go ahead and put that model in. It is a minus b over parentheses c plus t. Make sure we get that right. And nice thing about order of operations, it'll prioritize the b divided by the c plus t before it'll subtract. Very nice. I'm going to head and enclose that. Make sure it's all together. That's our model. Okay. And then we're going to do the difference between our model and our data. Our data was our log base 10 of p. And again, enclose that since okay, we still got more work to do. Sum square error. So sum of the square error. Error is this difference. We're going to do the square, which is little like that. Two asterisks for squaring. Did I match that correctly? Yeah, right there. And then sum square error. So then we need to sum it up. And nice thing about numpy again, we have np.sum, and that will just return us our little values of that we just did. It will give us a sum between the difference of our model and our data squared. So now we have this sum. See what happens when I try to do that. Nothing, because it's just inside our function, but we want to return that value. Still nothing. So make sure, actually, how do I want to do this? I have this vector of a, b, and c, and then we have those parameters inside our model. We still need to minimize them. So yeah, let's go ahead and do that. Minimize, since minimize, remember, was from scipy.optimize, again, great computational library. So minimize, let's go ahead from our function, sum square error, and usually with minimize, one of the arguments, or normally you should do is your guesses. So let's just guess what A, B, and C are. I don't know, 1, 2, and 3. How about that? So we have minimize. Oh, okay. There it is again. Make sure you shift evaluate everything. All right, so minimize is this nice little thing that returns a bunch of what's the word? Minimize returns. Anyways, it returns all these different things, but right here we have x, which is an array, and in that array we have our a, b, and c values. So obviously we weren't even close, but that's fine. Does it actually match our current? All right, it looks like we're outside those temperatures, but let's say we were. It should match the same experimental gathered parameters on the model from the website, but that's fine. This is what we got. Obviously, it's not going to be close since we're trying to fit our model from the data. Usually we make the data to fit the model. No, excuse me, that was wrong. Anyways, So minimize the sum square error, 1, 2, 3, and those are our guesses, and we're completely off, but that's fine. But now that we have these values, we want to make them equal A, B, and C. But if I do this, it's gonna yell at me because minimize obviously returns a bunch of different things, not just that X little X lot at the bottom. So what we want to do, uh, instead of just unpacking everything, we want to unpack the values at labeled X. So now, in corresponding order, each one should be the same as what it was earlier. Yep. And here we go. And 70, 50. Yep. Perfect. And now that we have A, B, and C, we can graph it on our graph. So let's go ahead and do that. We're going to do the same exact thing. Nice thing about writing code is that if you wrote it earlier, you can pretty much copy what you had. So X is still temperature. This time our Y, instead of log base 10 pressure, we can go back and we know our model was this. So we're going to type in just that. Equals A minus B over C plus T, close parentheses. And now we want it as a line, since that's usually what our model is, instead of markers, so we can distinguish from them. So let's go ahead, it should actually default. So I'm going to go ahead and shift evaluate. Oh, there we go. What is it now? X, C plus T. Oh, this needs to go above it so that it knows where to call it from. So let's go ahead and move this down. And now let's go ahead and do it. Okay, guess that wasn't it. numpy.float64 object is not callable. Perhaps we should try doing that. Oh, okay. All right, I'll see what this is about and I'll come right back. All right, I think I found the little error. I did not do a division sign. Yep. All right, that's the amazing thing about Python. You can always learn from your syntax mistakes since it's very hard to find. So I have this little red line. I'm actually gonna go ahead and change the color just for me. Marker color. Let's change it to an RGBA. And this is just something I've memorized since I've had to do it a couple times, but I believe it is 255 for all of them. And then A, so inside you can see RGBA. But we have in our parentheses, we have 4 different values that corresponds to RGBA. A is just the last value and it's opacity. Basically what you can see, that should be right. Oh, of course. So marker colors, I think. Oh no. What did we do? Oh, and parentheses probably. Marker color. Oh, this is hurting me. Sure they're equal. All right, then it's just marker color. Oh, rough sometimes. All right, 0.25. Trust me, I'll get through this. I'm learning with you. So yeah, RGBA. Here we go. That is our nonlinear fit data after minimizing our sum square errors. Next, we have to should do a linear regression of our data, and that's going to involve fitting our data with a model. It's going to be represented in a matrix. So I'm gonna say that again. We're gonna fit our model in a system of equations represented in matrix multiplication, and it's gonna be our design matrix times a vector of some variables we're gonna solve for, equaling our just say another vector. So let's go ahead and switch to the other tab I have. Should be right here. Perfect. We still got what we have earlier. Okay. I'm gonna erase that. Let's just call this, I don't know, linear regression matrix. So How do we do this? How are we going to represent it as a matrix? Well, the nice thing about matrices is that they're basically arrays, which contain similar types of information. And from earlier, if you remember, with arrays, we have numpy, and that helps us do a lot of things with arrays. Nice. So the problem is, how do we get a matrix? Well, we have our equation. What is our equation we have from our model? If you don't remember, it is log base 10 of our pressure is equal to A minus B over C plus E. And I've typed that into the code too when we were doing our nonlinearization, our nonlinear regression, excuse me, of our data. And they're equal to each other, and that's how we were basically solving for it in our function. Finding the difference between them, squaring it, getting the sum. That was our sum square error. And we minimize that sum square error to get our parameters. But here we want to represent this as a system. So again, we wrote the equation. What do we know? We know pressure and temperature. So we're going to have to solve for A, B, and C. And ideally, you would want your variables to be in that vector on the left side. So I'll just write it out like this right now for now. It'll be something like this. You have two matrices equal to another matrix, excuse me. And these two are going to be vectors. Vectors are basically just one-dimensional matrices. And if you don't know, excuse me, vectors can either be one-dimensional, meaning that if you know matrices are counted, or in notation, it's row by column. So 3 by 3 being would mean 3 columns, or 3 rows by 3 columns. Just a vector would just be, let's say it was n rows by 1. So it'd be an n by 1 vector. All right. So I'm getting a little bit ahead of myself, but that's what we're going to be working up to. So let's go ahead and try to fit this into the system. Well, so we have c plus t, common denominator, so I'm going to go ahead and just multiply that out. C plus c times r log base 10, okay, and a times our c plus t, and we just have minus b. So our goal is going to be trying to isolate what we know from what we don't know. All right, so let's just keep on multiplying this out and see where we go. We have c log 10 of p plus t log base 10 p, and then ac plus at minus b. So if we multiplied everything out, seems like it's gonna be pretty rough on how we're gonna isolate everything, since we have pressure temperature here, but we also have this pressure here. So we're gonna have to do some mixing around and little reorganization to see what we can do. Here, let's do here. I'm gonna rewrite this the right side on the left side, if that makes a little bit more sense, and I'm gonna move C log base 10 of pressure to the same side. So I'll just go ahead and do that. AC plus AT minus B. Actually, let's do it like this. AC, we have our AC, let's do C log, yeah, AT. You know what? Yeah, let's just write it. Okay, sorry. AT minus our C log base 10 of P. So AT, I move this over. Now we still have plus AC minus B. And the reason I did that, a little bit of thinking back there in my head, it actually makes it so that we have something we know with something we don't know. So we know temperature, we have A, so that's one thing, and we're finding A, so, excuse me. Finding A, and we don't, we know nope. Let's say that again. We're finding A, and we know the temperature, so that's one thing. We're finding C, and we know the pressure, another thing. I'm gonna go ahead and skip that. And now we have both things we know. That's another. So what is this? Like I said earlier, if you have, ideally you would have all these things in relationships where you could define them just with one thing you know and one thing you don't know. Here, it's a little complicated since we don't have anything to relate our unknowns with knowns. So that's something called a overdetermined system, which I'll get into once I write out the matrix multiplication. But go ahead and just call AC minus B, I don't know, just call it D. It's the next letter. Okay, so how are we gonna write this? Matrix multiplication. Okay, so we have our temperatures that we know. This from here, temperatures, and it's from N by 1. That's gonna be I guess the notation for it, but I'm getting a little bit ahead of myself again. But it's gonna be from all those temperatures to, let's say, Tn. All right, same thing here. We're gonna look at the pressure of what we know. So negative log, because of that minus, negative log base 10 of P1, and then goes on to, and we're just denoting that to however many times which is Pn. And now we don't really have anything to multiply this with what we know, so we're just gonna multiply it with ones. The reason we do that is because that allows us to return the same value, and once we know the D value, we'll have found the AC value, and then we can get the B. Very nice, because of how we have defined this part of the equation. If we hadn't defined this as D, it would be increasingly more complex on how we would have to write this as a system. So because we wrote it as D, we can just write this as 1, and it'll be D times 1. So we'll just find the value of D. All right, cool. So what are our unknowns in our vector? Well, what was times temperature? We have A. And then what was times the pressure? We have C. And then what was times 1? It was our D, which is equal to AC minus B. Again, D is a name to call it anything, but there we go. That's our left-hand side. Right-hand side, we have another vector, and that is equal to our temperature times our log base 10 of pressure. So I'm just gonna do T1, log base 10 of pressure 1, and I'm just gonna skip writing 2 since we know it goes on to n times. And that's because with matrix multiplication, at least in this case, I want to generalize and have it so that no matter what dimensions your matrices are, as long as your data, because at least in our data, we know how many data points we have, but we're generalizing to n amount, I guess, of those data points, so that we can basically apply this to if we had another set of data, let's say, excuse me, another set of data with a different amount of data points. So we're just using the n notation. So let's just actually, going back to what I said earlier, that write the n notation, or just a notation. So this is n rows, so n rows, 3 columns, so n by 3. This is 3 rows by 1 column. And then this is n rows as well by 1 column. So you can see it matches up. You have whenever you're multiplying with matrices, if you remember, this dimension must match the first dimension of the second thing. And order doesn't matter. You can't just switch them around, or else you'd have very different dimensions as dot products work. If you remember the dot product, it's just basically you're matching up certain dimensions of each matrix. So you'd be multiplying T1 times A, which is where that comes from. Make a log of 10 pressure 1 times C, this, then 1 times D. Here you get this, D. And it basically repeats until we get each little each row of this vector. Sip, because I've been talking a while. Excuse me. So we want to solve for this vector. And how are we going to do that? I mean, we multiplied it out and it works, but not what we were looking for. We're looking for AC and D. Excuse me. I think that water reaches triple point or something. So what we're gonna do is multiply. Like I said earlier, this is a overdetermined um, matrix, I guess, system. You could say a matrix multiplication. That just basically means there's more equations than we have unknowns. That's overdetermined. So right now it's kind of unsolvable unless we did a neat little trick by multiplying by the transpose of our design matrix. We call this our design matrix next to our vector that we're solving for. So I'm going to say that again, the transpose is when you flip the dimensions. So let's call this all these names so we know what we're referring to. Let's just call this M for matrix times our vector is equal to our, say, our B matrix. So we have M times a vector equals our. So what I said earlier, we're going to multiply by the transpose B times our M vector, and then same thing, what you have to do on the left, you have to do on the right. The order does matter. I'm going to show you why. So n by 3, the transpose of that would be 3 by n, and then you would have that times n by 3 give you a 3 by 3, right? Because the n's cancel. Same thing of over here, how the 3's canceled. Not necessarily they're canceling as in data points are missing, but in how we multiply the dot product out, that is how we got the resulting vectors. The same thing happens here. Even though n could be infinity, it multiplies out. Well, actually, it wouldn't be infinity. We're just denoting it as a number. But it could multiply out, and we have a 3 by 3. And again, this is still a 3 by 1. Then we have that equal to our m transpose, which is 3 by n times 1. Same thing over here becomes 3 by 1. Let's see if it does match up. So 3 by 3 times 3 by 1. Match? Yes. You'll have a 3 by 1. Cool. So we multiplied transpose on both sides of our overdetermined system. And now we can use our linear regression coding in Python to solve for this vector. Cool. All right, so let's go ahead and do that. Switch tabs. Let's close this and go here. Back to our little graph. Okay, this is recording night. Okay. So we have our graph. What do we need to do next? So going back to our little equations over here, we need to multiply the transpose against our matrix and also multiply the transpose for our design matrix, the second matrix, our array on the, or our vector on the right hand side, which of full of what we know, our temperature and our pressure, log base 10 of our pressure. All right, so let's go ahead and actually write that down. That was just for my reference, in case you forgot to, but let's go ahead. So we need to define our matrix. And how are we going to do that? Well, numpy also has something called np.concatenate, and this is just basically concatenating an array, again, a function, an array on the same axis. So the default is, I believe, row-wise. So we don't really have to add anything. So we're going to concatenate some array with, or an array with our values. I believe it is temperature. Go back, temperature, negative log 10 of p, and our ones. So we're going to do something called np that ones, ones like, yes, np that ones like t. That is also a pretty neat function that numpy allows, where we just make a bunch of ones. That's basically what it's saying, a bunch of ones like the similar shape and size of t. And t would be, excuse me, our data points from over here. from start to end. So it's just basically going to match the same number of data points we have. So that's our matrix. If I try to shift evaluate this, yeah, it's not callable. It's not going to do anything. So we need to assign this little variable, what we called it earlier, our m for matrix. Oh, we did so. Oh, I know. Syntax. So arrays, make sure when you're doing arrays, they are with brackets. So that is what we use to denote them in coding language of Python. So now we have m. I wonder if I should show, if I remove this, it should show the right, perfect. So it shows our temperature, log-based tens, a negative version of them, and ones. Cool. And then we set that equal to our m matrix. So from earlier, what I said, we're going to multiply our, let's go back, we're going to multiply our m by our transpose, find our vector, and we also need to do that to both sides. So I'm going to say it in this statement. We multiplied the transpose of our design matrix, m, to both sides to solve this overdetermined system. Because as of yet, or as of this point, it was pretty much unsolvable. All right, let's do that. Back. Cool. All right. Matrix multiplication. What do we need to do? We're going to do m times, actually m dot t transpose matrix multiplication, which is the add sign, times m. And then we're also to do m transpose multiplied by b. And if you remember, b was our temperature and our pressure. So actually we need to use parentheses, or else it'll do the matrix multiplication first. So it was temperature times our log base 10 of b. Cool. And if I write this out, I wonder, okay, I'll just show it right there, which is some pretty weird numbers, since we want to linearly, excuse me, we want to algebraically solve this. So what we're going to do is something called np.linalgebra solve. Put that in parentheses. Oh, here we go. Syntax. There we go. Perfect. Oh, syntax errors. Okay. np.linear algebraically solve, again, a function from NumPy. Go ahead and look at all the functions in NumPy, but again, that's another function we'll be using. And it just solves this system we have. It'll solve for the vector we were looking for, our vector, which was our ACD vector. And those are exactly the outputs that we're getting right now in our array we got. So we have A, C, and D. We know A and C should be pretty close to what we had earlier. I wonder if I can just print. Let's go ahead and see what they were. So we had 10, 1756 is B, negative 36. So we want A and C, 10, negative 36, 10, negative 34, pretty close with linear. So this is our D value, ACD. So how are we going to solve for D? Let's go ahead and unpack that again. So if you remember what I said about unpacking, let's call them names. Unpacking basically assigns names to the exact positions in the same order of your array. So we had A2 first, D2 second, and D was our third. Again, arbitrary. I know it's A, C, D in the original vector, but we have to call them something else, or else we'll get a little confused with up here. So, all right, now that we unpacked it, we have to solve for B. Let's just call it B2. So we have to solve for B2. Well, going back to our original, yeah, relationship right here where AC minus B equals D. Let's go ahead and solve for B. So what is B? AC minus B equals D. Solving for B, we'd have to move everything over. So we have, let's just move B over there, D over here. Simple step, we have AC minus D equals B. Pretty easy. Okay, and then let's put that into our code. Right here. B2, again, differentiating from the first B we had is A2 times C2 minus D. And shift enter. Let's go ahead and print what it was. B2, 1771. And, oh, where is it now? I think I deleted it. Let's go A, B, C, view them again. Perfect, 1756. Pretty close, 1771. All right, cool. So now we have our A, B, and C values again. We're gonna do the exact same thing. All right, so go ahead and merge these. We're gonna go ahead and merge these cells, and I'm just highlighting them, right clicking, and then merge selected cells, and I'm gonna move them up using these arrows on the side. You know what? I think I forgot something on this graph. I'll get to it. I think, yeah, it's a couple things, but it's okay. So let's just go ahead and graph it first. So we're gonna do the same thing we did earlier. Fig1.add scatter x equals t again, and this time we have our new a, b, and c values. So I'm just gonna write them as we wrote them. Sure, hopefully not to cause another little syntax error. And let's go ahead and graph it. All right, it's pretty much similar to the other one. But you do notice that there's a little jaggedness right here where it's connecting these points, and it's kind of like lines. We don't want that for our model. So let's go ahead and make something. We want our model to be fit to, instead of interpolating, excuse me, our model shouldn't, it was a little weird how we did this, but instead of our model working between each point and matching our experimental data points, we want to use those new parameters of A, B, and C to work for any temperature that we have. So let's go ahead and do something like, all right, for T of temperature for plotting, just for plotting purposes, so it's not a line, we're gonna do something, assign that to something called np linspace. Again, numpy, very nice, lots of functions. np linspace basically returns equally spaced values, or linearly, yeah, I think that's right, linearly spaced values between a certain interval we're gonna give it. So I believe the first three parameters are start, stop, and number of points. So we're gonna go, let's say, what does our temperature start at? Like 293. Let's go like 290. And then maybe just to match our data, go 700 since that was 650-ish. Let's go 700. And let's say it's 100 data points. Enter. It's not going to do anything since we actually didn't change our graphs. So let's go ahead and change our models. We're going to have to change these to plot here, plot here, and same thing here, plot. Oop, go plot. Cool. Now you get a little non-curve, and you can see here, I can just comment this out. It will be the same thing for our linear. You know what? You can't actually see it. Let's actually name the label. I guess I forgot to name. Don't do as I do. Do as I say. So we're just gonna call it, what was it? This is our Antoine string Antoine linear. This is our Antoine nonlinear. This is our data. Should show up perfect. Cool. So now we have graphed both linear regressions and nonlinear regressions. See, they're virtually similar from afar, but if we get closer and closer, go to a point. See how they're slightly different? Nonlinear is actually closer on this side. You might ask which one's better or which one's right. Well, the answer to that is actually a little complicated. There's no right or wrong. It's dependent on what the data gives you. Data always has some little error, standard deviation, assuming it didn't just randomly generate some perfect points that would somehow match a trend. But in this case, there has to be some standard deviation in our data that we collected from our file, that our .csv file. So really, it just depends on the type of experiment you did and your error and accuracy within it. And with the error and accuracy, it comes in how big or small the experiment you were doing. Let's say, I don't know, we have a little scale for measuring weight. I step on it and it reads to maybe 0.1 of a pound. Great, so that's about the accuracy of reading the weight of me. But then we scale up. Let's say we have a truck, or I don't know, an elephant, something huge. Obviously, that actually, if it measures to the same accuracy as 0.1, well, that's a pretty good scale. And probably with technology nowadays, you probably reach it now. But the point I'm trying to make is that scaling up or scaling down, you're gonna have higher or lower, um, let's say, ranges of error. So whenever you use linear or nonlinear regressions, it's not just if I can solve a linear system or representing it in matrix multiplication and then multiplying by the transpose to find our vector of unknowns, or just using nonlinear regression because it's not linear. You also have to keep in mind the error in your experiment and whether or not which regression was the right choice in terms of your experiment. And great, that has my little walkthrough of little bumps in the road of syntax errors and matrix multiplication for linear and nonlinear regression. Next, we're going to dive a little bit deeper into the Antoine equation, and hopefully we're going to solve for some unknowns using a very common equation probably heard of, the ideal gas law, and using those relations to find unknown within given unknowns and given unvariables. Actually, let's just say initial values. All right,